Module 1, Lesson 15, Rotations, Reflections, and Symmetry. As usual, we're starting off with some vocabulary, and some of this is already known to us. For instance, a regular polygon, we know this one, is both equilateral and equiangular. That means all of its sides are congruent and all of its angles are congruent, which also means that all of your sides have equal length and all of your interior angles have equal measure. So everybody's congruent. The symmetry of a figure is a basic rigid motion that maps the figure back onto itself. So basic rigid motions are rotations, reflections, and translations. We are going to be concerned most with reflections and rotations for symmetry. Line of symmetry is a line that divides a figure into two congruent parts. A figure is said to have line symmetry if there is a line or possibly multiple lines that the image, remember that's the second part, when it is reflected over the line becomes itself. So our image is exactly the same as the pre-image. The line of symmetry can be thought of as a reflection across itself. Now, some important ideas here about line symmetry is that every point on one side of the line of symmetry has a corresponding point on the other side of the line of symmetry. Everybody has to match up, and this is done with a reflection. Your line of symmetry is equidistant from all corresponding pairs of points. Rotational symmetry is a rotation of the plane that maps the figure back to itself. Now, these rotations need to be greater than 0 degrees, but less than 360 degrees. Because an identity symmetry is a basic rigid motion that maps the figure back onto itself. It is a special transformation called the identity transformation that maps each point back to the same point. So this is our 360 degree rotation, and we'll see how that works. Now, a look at our types of symmetry here. The figures are going to be unchanged after a reflection across a line or a rotation about a point. Your figure has symmetry if there is an isometry. That means we have congruent segments, which means they are distance preserving. And we have congruent angles, which means they are angle preserving. Line symmetry, also called reflectional symmetry, occurs if there's a reflection of the figure, which is its own image. The line of reflection is also called a line of symmetry. It divides the figure into congruent halves. So let's look at, we have an isosceles trapezoid here, and if we consider this to be our line of reflection or our line of symmetry, think of reflectional symmetry as a fold. So if we fold our trapezoid here across the line of symmetry, it's going to match up left side to right side. But you know that when you're doing a reflection, all points have to be reflected. So the points on the right side also reflect reflect back to the points on the left side. So even though it's a fold, it's kind of a fold both directions. Rotational symmetry is if there is a rotation of 180 degrees or less for which the figure is its own image. So if we look at our triangle here, we can rotate this vertex, and if we spin our triangle around, it's going to land on this vertex here. This will be our image, and it becomes itself again. This rotation is 120 degrees. Now, if we think of a segment, we can rotate a segment about its midpoint. So these would be congruent. If we rotate a segment about its midpoint, we can go 180 degrees. The angle of rotation is the smallest angle needed for the figure to rotate onto itself. So for our segment, it's 180 degrees. For our triangle, it's 120 degrees. And we will look at a few other figures here in a few minutes. Kind of an interesting point to note is a figure with 180 degree rotational symmetry also has point symmetry. That means that each segment gets rotated 180 degrees about the center of rotation, which is right here. For our parallelogram here, we can rotate 180 degrees and it will lay on top of itself again. It's mapped back to itself. So this has rotational symmetry of 180 degrees. So this has point symmetry. A square, which has both 90 degree and 180 degree symmetry, also has point symmetry. So let's look at a square. And if I rotate this point of my square 90 degrees, it maps back onto itself. I can also rotate this point 180 degrees and it maps back onto itself. So it has 90 degree rotational symmetry, 180 degree rotational symmetry, which then means it has point symmetry. Our major concepts for this lesson: how do we identify lines of symmetry? So we are going to look for ways that the figure will reflect across a line onto itself. The hexagon here will reflect onto itself across each line that passes through the midpoints of each pair of parallel sides. So here are two midpoints, and here is our line of reflection. Can you see that it just folds over like that? And this is true for the line that passes through this midpoint and the line that passes through these midpoints. We can fold our hexagon both directions over those lines. Our hexagon also reflects onto itself across each diagonal that passes through the center of the hexagon. So here is our center, and now we are folding it on the vertices. So we are going to add this line of reflection, this line of reflection, and this line of reflection. So now we found all the ways that we can reflect our hexagon, and now we count up how many lines of symmetry there are. So we start here at the top: 1, 2, 3, 4, 5, 6. Be careful to count each line only once, because this line down here, right here, that is the same line that we counted as line number 1. So we don't want to count that. So a regular hexagon has 6 lines of reflectional symmetry. Our other type of symmetry is rotational symmetry. Now there's some important ideas that go along with this. The center of a regular polygon is the point that is equidistant from its vertices. And we are going to form angles that join the symmetry with, or the center of rotation with the vertices, and your pre-image pairs must be congruent. And we'll see what that means in a minute. The center and vertices form n congruent triangles, and n is just the number of sides of our regular polygon. And the angle of rotation of a regular polygon is just 360 degrees, because it's a circle, divided by the number of sides. So let's look at an example. Our angle of rotation is determined by connecting the center of rotation. It's right here in the center of our pentagon. Connecting the center of rotation with corresponding vertices. So point X is the center of our regular pentagon, and it's divided into 5 congruent triangles. And now we find the angle of rotation by taking 360 divided by 5. Because it's a regular pentagon, n equals 5, and we get 72 degrees. So we know that each one of these is 72 degrees. So what does a 72 degree rotation look like? Well, if we take point T and we rotate it 72 degrees, where does T end up? T ends up on point N. So the image of point T is point N for a 72 degree rotation. We can also rotate segments. Let's do a 216 degree rotation of segment TN about X, our center. Well, how far are we going to go? Well, 216 divided by 72, because we know that's one rotation, is 3. So we are going to rotate point T 1, 2, 3 places. That would be T prime. T prime is P. And we are going to rotate point N 1, 2, 3 places as well. So it ends up there. So the image of segment TN is segment PA.